All right, well, welcome everyone. It's 7:01, so I'm going to get rolling because we have a speaker tonight and a few things to talk about. My name is James Burke. I'm one of the co-founders of Space Northwest, as well as on the board of directors. My day job is I'm the executive director of the Mars Society. We're a global nonprofit advocating for a human mission to Mars. We operate research stations in Utah and the Canadian Arctic. And I'm also a former Microsoft engineer. I worked there for 20 years before I started doing the Mars Society full-time a year and a half ago. And this is the Space Data Hackers Meetup series. We meet every month. We are helping people that have technical backgrounds understand how to work with space-related data sets. You can always find our meetup schedule on the website spacedatahackers.com. We use Eventbrite, we use meetup.com, Facebook to promote this series, as well as other means. We also, if you go to that website, we also have a wiki, and that is a great place to learn about how to work with space-related data sets, get some free training, and really start your journey or continue your journey of learning about space and how to work with data that's space-related. So the agenda tonight, we're going to have a presentation by Clive Cook of Precursor SPC. We'll get to that in just a moment. I also want to highlight that we love to show community projects at this meetup series. So we always have a little bit of time for folks that want to share the work that they've done. And we encourage side projects to be started through this meetup series. In past years, we had a team looking at how to predict wildfires using satellite data and AI, a very worthwhile area to work in. And we'd love to hear other ideas of projects people would like to work on and make connections through this meetup series to start.
Fabulous.
And then just a little bit about Space Northwest, the organization that I'm part of and that is organizing this meetup series, as well as other things. We are a nonprofit 501c3 organization in Washington State. We partner with all of the local aerospace companies, nonprofits, the local city governments, such as Redmond and Kent, which have space focuses recently, and the State Department of Commerce. We're actively seeking volunteers to run our events, such as this one, as well as helping with marketing, social media, and other overhead that any nonprofit needs to deal with, as well as fundraising. So if you'd like to join us, please send an email with your notification of interest to info@spacenorthwest.org. And so now let me introduce our speaker tonight. Clive George Cook is the Chief Executive Officer of Precursor SPC. Clive is a machine learning and AI professional and a serial entrepreneur with extensive experience leading high-growth technology-based initiatives. He has achieved multiple successful exits, including to Dell, Lucent, and Banco Santander in fintech, telecom, and mission-critical systems, respectively. And he still does a lot of coding. That's awesome. I also do a lot of coding still. Clive holds a Master's of Computer and Systems Engineering and an MBA. So welcome, Clive. The floor is yours.
Fabulous. Really nice to be here. Been quite looking forward to this. I'm going to share my screen here to show you guys a bunch of stuff that that we do. Slideshow, play from start. Okay. So Precursor SPC, we're a Washington-based company. SPC is a social purpose company, means we are a Class B company, which really means we're a for-profit company with a stated social mission. And that social mission is specifically to use our technology, nowcasting, to save lives and billions of dollars. And I'll show you how that works. First off, I don't want to use a lot of jargon, but I will use two words that that are important to what we do. The first word actually is also the name of our company, and that's Precursor. So my two co-founders, Dr. Pierre Richard Corneli a brilliant atmospheric physicist, and Dr. Friedemann Freund, a material scientist from NASA. They, after the 2010 earthquake in Haiti and the 2011 earthquake in Japan, which caused a lot of personal tragedy in their lives, asked themselves what they could do to lessen the impacts of these catastrophes. And as you would expect from physicists with their background, they looked at the problem and the challenge quite differently and uniquely. And they discovered something that everyone else had missed. And that was, prior to an earthquake, there is a measurable buildup of energy associated with that earthquake called or referred to as earthquake precursors. So if you think of the 2011 earthquake in Japan, that was the equivalent of 2 million Hiroshima-class nuclear devices going off simultaneously. But that buildup of energy took months. And you can measure that buildup of energy at the ground, but more interestingly, or more uniquely, in space. Because as thousands of cubic kilometers of rock come together under extreme stress, what that does is cause a source of electromagnetic energy to travel from that point of stress to the surface of the Earth and interact with the electrically charged ionosphere, low Earth orbit. So what we have done, we Precursor SPC, is to use AI to nowcast the environment of low Earth orbit and to use that to forecast earthquakes and tsunamis and other space weather events. So that's the intro. Oh, we're not moving. Why aren't we moving? There, let's try that. So you all know this stuff. You're involved in space. But what the world of space, while we're pushing the frontiers of space, is really, from a data perspective, kind of sparse, right? We have these models that we parameterize with instrument measurements, and they build this environment that tells you, on average, what is happening at an average altitude, at an average time, at an average day. And the net result is you get an average. But now, with the proliferation of space-based systems, multiple space-based systems, with the proliferation of sophisticated ground-based systems, and I'm talking about radar systems here, we can use both of those ground and space-based systems to get a very high fidelity, very high resolution representation of the low Earth environment, strictly, purely on data. We do no longer need these models of Earth systems that tell us, what it's kind of like on the average over the whole hemisphere. And, it's going to change like this because it's changed like that for the last 50 years. That is the old way of thinking and produces, as I said, an average result. That is not what is needed today for advancing our aspirations in space. Space weather, as you can see here, affects every aspect of the space economy. Not just in space for the space operators, both national security and public safety, but also for those private space operators, but also for terrestrial organizations, power utilities, comms, pipelines. All of those are impacted by space weather. And when you look at space weather differently and understand not only what is coming down from space and impacting both the space weather environment and the terrestrial environment, it's also understanding and recognizing that there are phenomena in the earth or at the ground that dramatically affect also that environment of space. So space today, the space weather environment, how that changes dynamically in real time, dramatically affects communication, dramatically affects space, national security, applications, tracking and discrimination of radar for both aerospace as well as space, as well as adversarial operations, and affects the orbits, specifically low Earth orbit, of those assets that are important to our everyday. We all heard about the 2022 Starlink loss of 43 or 40 odd satellites. So they launched, as I'm sure you know, into based on the models that they were using, they launched into an average environment saying there would be mid to low grade geomagnetic storm at that deployment altitude, and everything would be fine. What really happened was they launched into two kind of low grade geomagnetic storms that in superposition created a significant drag at that moment, at that altitude, at that hour on those satellites, causing them to fall due to the increased orbital drag into the Earth. They were blind to the space weather. So what Precursor SPC has done, sorry, I got ahead of myself there. What Precursor SPC is doing and is providing based on data is to take a completely different approach that removes the idea of let's have models of Earth systems, whether they be in space or in the oceans or in the ground or whatever. Just use data, massive collection of data, and machine learning, combine those and move away from these physics-based empirical models, which impose assumptions and biases upon the approach such that you're never going to see any real-time changes in the environment using this model-driven approach. This is why the Starlink didn't know, or SpaceX in this case, didn't know that there was a geomagnetic storm in superposition at that location, because the model said it was going to be on average. That is why there is no ability to recognize the pre-earthquake signature in space coming from these thousands of cubic kilometers of rock coming together under extreme stress that are representative of the energy buildup in space, because the models don't think that way. The models do not have a representation of an earthquake in them, period. So what we developed and said, get rid of the models, get rid of the biases, introduce something. Because of the proliferation of assets in space and on the ground, you can come up with a data-only driven approach that is ultra-high resolution, ultra-high fidelity at all altitudes, that will give you in 4 dimensions, meaning a 3D voxel in space and a changing over time in very tight granularity, the ability to resolve all of that data in real time using machine learning, and use that representation, the nowcast of the environment, to dramatically improve your performance in space, understand the impacts in space, as well as understand those signatures that only occur in real time that are not contained within the models. So this is oh, sorry, I got the wrong version here, but this was supposed to be a video. I apologize. I got the PDF version. This is actually a video of a real-time auroral event. First time it's ever been done over Northern Europe that we did for US Space Force that dramatically shows and changes in real time the impacts of the changing ionosphere, which is that colored map on the bottom. The impacts of the ionosphere on specific spacecraft operations, spacecraft tracking, comms, remote sensing, power utilities on the ground, GPS, GNSS, by using multiple data sets. So we're using GNSS data sets. We're using LEO beacon satellites. We're using GLONASS satellites. We're using radars on the ground, incoherent scatter radar and ionoson radar. All of these we combine to give you in real time this picture of the changing ionosphere. What you see here is a slice of that specific ionosphere at that time. What we actually have is a four-dimensional representation in real time that we give to different customers so they can know in real time what the environment is going to be, whether it's going to change rapidly or it's just changing in the normal course of the day or evening. By using this real-time data capture, we can also flip that around and literally use the ionosphere as a giant sensor. And that giant sensor can be used to detect the buildup of energy prior to an earthquake. So you see here, this is a picture of the ionosphere over Japan before the 2011 Tohoku earthquake. You see the elevated TEC levels, total electron content in the ionosphere, already elevated, starting at that light green color and moving over this 10-hour window, increasing significantly, orders of magnitude increasing during that window, which is exactly representative of the buildup of energy prior to an earthquake. And by combining, this is all done with space data. By combining this space data with machine learning AI, we can tell you not only the buildup of energy, we can tell you the anticipated magnitude of that earthquake on the ground, and we can give you the anticipation time hours and days in advance. That is only possible with space data. Who would have thought space data can give you that information about a ground-based phenomena? That is powerful. And that's because we use multiple space-based systems and AI to bring all that together. So this is a ConOps of our of the work we're doing, taking multiple systems, pulling them together, data from government, private, and proprietary systems, pulling that together into the AWS cloud in real time, and that's key, and using that to perform what we call a data assimilation of the ionosphere to capture in very high resolution, both in space and time, the changing ionosphere, so we can tell that to aerospace companies as they fly over the poles. We can tell that to SpaceX as they launch their Starlink satellites. So we can tell that to national security organizations for their work. And we can tell that to FEMA and DHS that there's a buildup of energy over this region prior to an earthquake. That's all I got. Make sense?
Awesome. That was a really great presentation. Thank you, Clive. Does anyone have any questions? Go ahead, Michael Patrick.
So I'm not particularly, I'm right at the moment, my problem right now is synthetic aperture radar, how well from orbit can it see a U.S. Army battlefield presence in terms of the electrical generating grid that they set up for a forward operating base or whatever. So they bury the cables and stuff, you know. So I have like this really Frankenstein Swiss cheese knowledge of the subject matter. It's way complicated. So when I'm seeing that graphic of Japan go by, I'm thinking, in my mind, what I'm wanting to see is next to it the seismicity map. We here in Seattle, we live in a rather seismic, so we get the big ones and they're talked about, but at any given time, I just look like right now there's a couple of dozen Richter 1 or less that are going on probably within 60 miles. I was hoping to take a screenshot to show. So there's this, excepting the really major events, there's always this constant, activity and energy buildup going on. And so what I was looking to be convinced with is the correlation of this intensity with the level of seismicity alongside of it, because of the natural variation in the ionosphere or whatever. That only for me means something when compared to something else. And then what follows on the tail of that is the signal to noise ratio and the correlation. It's never a linear, and the problem being a geographer and doing visualization symbology and stuff like that, whenever I see a gradient map, is how is that linear gradient, or whatever, map to the intensity that is significant for the problem at hand. So whatever threshold level, etc.
Yep.
And so can you speak to those things in a little more detail?
Absolutely. Great question, by the way. Really, really thoughtful question, and kind of one of the deeper questions. So I applaud you on that. So we're measuring the buildup of energy over a region. What I showed you was the buildup of energy, but we have other techniques to narrow that down into a very precise grid of location on the ground, using both the space-based capability and the ground-based capability. So we combine both of those to give you a very tight resolution at the ground of the energy located within a specific geography, literally plus or minus latitude and longitude, plus or minus 25 kilometers, pinpoint accuracy. Seismicity, as you said, to compare that with seismicity, is a mechanical event. It's the rupture of rock or the movement of rock.
Right.
Right.
I only picked it because
it
was on the top of my.
Yeah, we don't measure that at all. That is the truth, if you will, of our approach, because we're measuring this stream of buildup of energy, which has associated with it these precursor events or precursor phenomena, which we use with our machine learning capability to establish a timeline, a sequence that builds up always builds up prior to the earthquake. And that's how we now cast. And then the truth is the seismic event. So we're never comparing.
So if you closed,
go ahead. No.
So if you close the loop, okay, so given the Earth is big and we live on the Ring of Fire, there are some major 7-point,
Sure.
magnitude happening somewhere on the planet, some with actually more regularity than is comfortable. So if you zoomed in on those areas and loop back to validate the, the model, not just in spatially, but in terms of time and response and that sort of thing. Is there
Yeah.
any
So we've
quote
done,
unquote ground?
so first off, our capability is regional. It's not global, right? We have to,
Right. I'm just saying it's somewhere on Earth.
so we've done multiple programs in 6 different geographies in Alaska, California, Peru, Italy, Taiwan, of this exact thing. And for over those 3,000 days of putting in place both space and ground-based capability to measure that buildup of energy, the precursors and the event stream, we have successfully now casted over 50 seismic events with a correlation accuracy of over 95%. Over those 3,000 days, we had 3 false negatives, meaning the equipment went down in this particular case, and we couldn't definitively say nothing happened, though nothing did. And we had 2 false positives where we missed the window that we were now casting for by 12 hours. So we've proven this capability repeatedly in different geographies, different programs with different sets of data, and always running that through our now casting capability. Our plans are to go forward are to put this down in a permanent infrastructure in the state of California first. Why California? Because it's a $3 trillion economy and 40 million people, and got Vandenberg Space Base, and it's got, a massive energy grid that is impacted both by seismic events and space weather events. So that's what we've done to prove out the ability of to use space weather data as a sensor, or use the ionosphere as a sensor. And then we have ongoing programs with DoD specifically to use that for various national security applications, and we'll leave it at that, that they are using it for, to give them real-time insight into the ionosphere for some of the things that I mentioned up there. Does that answer your question?
It gets there, and I should probably ask if anybody else has a question. I tend to monopolize.
Anyone else, just raise your hand. Otherwise, we'll keep going with Michael's excellent.
I have a question.
Go ahead, Manuel.
I understand space weather data is important to all space operation, meaning that data availability and integrity is very critical, right? So I guess my question is, what's your take on cybersecurity to protect that data? And is your organization taking space cybersecurity into consideration?
Excellent question. We, from the outset, because of our data-only approach, we have incorporated different, we've incorporated cybersecurity principles into our data capture, our data receipt, and into our processing of that data in the AWS cloud or in the Gov cloud. We use everything we do is all the data manipulation we do in secure facilities. So it's very much baked into what we're doing from the start. That said, cybersecurity is a very much an evolving challenge for everybody. So we're continuously trying to incorporate the most current thinking and approaches into our products. I'm sure we're not there yet, but we continue to try. We're pretty ambitious as a company in launching our capability, but we're also very constrained, as I'm sure many people are, by resources. So we're doing what we can. We've baked it in from the beginning. We need to continually be diligent about making it a priority.
Great, thank you.
You're welcome.
Anyone else? Go ahead, Joe.
So is there a way in an adversarial relationship for someone to wreck your signals, basically, if they thought to jam your signals, if they think that it's being used against them? Is there some way that they can also create a field of their own? Like if you think science fiction, some kind of a force field or a shield?
Or HARP.
You definitely HARP. We're actually working with the University of Alaska, which has taken over HARP. So we work with those guys very closely, actually. So
Can you tell us just a little bit about what HARP is for those of us that are laymen that don't?
Weather control.
Okay.
HARP is a large facility in Alaska. I think it's 400 acres of a high energy system that sends signals into the ionosphere to modulate the ionosphere at different parts of the globe. The ionosphere is the shell that surrounds the Earth, 50 kilometers to 1,100 kilometers. And that shell, you can use that shell to bounce signals anywhere in the globe. And HARP is a mechanism to using man-made intent, whatever that is, to modulate the not only to transfer that signal from Alaska to somewhere else, but to modulate it at the point of intention. So the Russians have that, the Chinese have that. It's the same. You basically put it over a battle space and it blinds everybody, it blinds radar, blinds communication, or shuts down communications. And some say, like Michael, that it can also change the weather. I have no comment on that one.
Well, it's in the actual, so I've read the actual patent. The patent's kind of really funny to read. It's actually kind of humorous because you can see this guy sitting behind a desk just thinking of every conceivable use it could be used for. So in actuality, it does control the weather in the atmosphere, but atmosphere that at levels where it's pretty much a vacuum. You know, it's not like moving hurricanes around and stuff like that. And
it's not terrestrial weather. It's not going to change the precipitation or the humidity or any of that sort of stuff.
And its genesis was out of, you know, in the early days of ICBMs, it was as an anti-ballistic missile possibility. Is could you screw with a guidance system of an ICBM coming? That's how it ended, or one of the reasons it was put into Alaska. Aside from being near the North Pole, where you have optimum capability to send stuff, you know, lots of different directions.
And this is why the high fidelity real-time representation of the ionosphere is so important for national security applications, right? Because, you know, missiles passing from North Korea into the Pacific Ocean, you know, they go up really high, they go into the ionosphere, and the electronics in there and the guidance in there is directly affected by the ionosphere, as well as our ability to track it. So it goes both ways. So.
Go ahead, Michael.
So the Van Allen belts in the ionosphere, what's the relationship between those, and does it affect your system?
There is some coupling between the Van Allen belts and the ionosphere. We don't, if it is noticeable with high gradient changes in the ionosphere, we will, because of our high resolution capability in both space and time, we will know that and represent that. That's kind of
Yeah, I was sort of curious if you were looking the other direction other than down, because of that coupling, if there was, that could induce other effects in the
Yeah,
measurement.
absolutely. That it definitely induces other effects up there. There's a lot of interesting things going on up there. But, again, it's just about gathering the data and not making assumptions with models, right? Because the model assumption by definition is going to be wrong at least 50% of the time, right? It's an average, right? Probably wrong more than that.
Well, in all fairness, I'm kind of a fan of weather forecasting from the very beginnings. That Norwegian who came up with the first, grid over Europe, and then most people don't know that, like, the weather forecasting was one of the first uses of when they turned on the first computer at Princeton, was running weather simulations. And so Lorenz at that time, you may have heard the phrase the butterfly effect.
Yep.
In other words, as you go outward in time and spatially in resolution, etc., you reach kind of a horizon of where everything becomes noise and chaos. And I don't necessarily know, it would seem to me that geophysical models in your system complement one another, in the sense that you're picking your regions and stuff. Well, which places should you keep an eye on would obviously probably be informed by geophysical model. But then again, if you want to look out, even so, depending on if you're looking far forward or immediately, you would probably wish to be informed by both.
I agree. You want to be informed by both. And what our approach is, the nowcast of knowing exactly what is happening at this moment in time is the foundation for forecasting, as opposed to the other way around, which is, we're going to forecast the impact of some coronal mass ejection, and, who knows what's going to happen. We're like, this is what happened. This is what's happening at this exact moment. Using that, we can forecast the impacts, because that's the only thing that's important, is the impact, because we know exactly what's happening now, rather than assuming something will happen based upon a model. So I think we're saying exactly the same thing.
Yeah. So at the moment, that nowcast for you, is that in terms of seconds, minutes, hours, days?
It's content or environment dependent. So for the space weather nowcast is generally valid for 2 to 3 hours.
Okay. Enough, more than enough.
And the earthquake nowcast is valid for, depends, 3 to 7 days, which is today. You may know this already, but today for earthquakes, you get a 25 to 100 year hazard model of what might happen in the state of California at some time, and it's going to be really big. Or you get a shake alert, right, which tells you 10 to 30 seconds after the earthquake happens that you're going to feel a shake 25 miles away. So that time, that human scale time of, weeks, hours, days, is the gap that we fill with nowcasting.
And to some degree, when it comes to predicting earthquakes, there's a psychosocial huge element involved with false alarms and stuff. As you cry wolf twice or 3 times, people start ignoring it.
And this is why
there's a hyper
exactly why the shake alert thing is failing in Japan.
Yeah.
That's exactly why. You get random, and people are like, you also get the shake alerts for the small ones. It's like, I don't want to be bothered by a small one unless I'm like, some organization, like, we're doing some work with Taiwan Semiconductor, and they're doing, 20 nanometer feature size. And when you're doing 20 nanometer feature size, the little shakes make a huge difference. So they want to know about that, but the rest of us, kind of care less, right? But you have to get it right. This is absolutely for the space weather for the national security one applications, you know, you're correcting for anomalies and inaccuracies in tracking or radar, and that's super important. You want to reduce that as much as you can. But for earthquakes, you know, you don't want to have those false alarms, as you said, right? Because it makes a big difference to the confidence going forward. So we've intentionally, you know, I'm sure none of you have ever heard of Precursor SPC before. I'm certain of that. But we've done over 50 earthquake nowcasts with, you know, virtually 100% success. But we haven't publicized any of that because what we're doing now is continuing to build the confidence in our nowcasts so that when we launch it, there is a low likelihood, not zero, but a low likelihood that we would miss it.
There was, oh, pardon me.
Go ahead.
There was one data point that you said was a miss. And was that early or late?
They were both early.
So in some senses, that's better than being late.
Yeah, I would agree with you, but others would say late is late or early is early. They're still misses.
Yeah.
But you know, 12 hours, like we got the location right, we got the magnitude right. We just missed it by 12 hours.
So other than actually earthquakes, is just ionospheric exploration and thinking in terms of cartography, is there any direction going to mapping the ionosphere in its variations as a whole? Things like the South Atlantic anomaly, and you know, there's things that play havoc with aircraft community, those transoceanic aircraft communications and things like that. And that might segues to the second part of the question, is where's the business opportunity? In other words, who's going to pay for it? Because it's like eating right. You know, it's something you should do, but it's nobody's problem because it's so broad. And then who's your competition in this? What are the headwinds that you have? So
there's a lot there. Again, I love your questions. They're really, they're good. We haven't done any work on mapping the ionosphere globally, right? You know, there are distinct environments in the ionosphere, the polar regions, the equatorial regions, and then the mid latitudes are very different. And then there's different anomalies, as you mentioned, the South Atlantic anomaly. And then everyone's scared of these Carrington events that may or may not ever happen. What? But we haven't done that. You know, as I mentioned at the outset, our capability is regional at the moment. You know, we're a relatively lean organization, and we're very focused on a couple of use cases. Those use cases are for the government, for some national security use cases, and for providing this capability to high value asset owners, whether those are rocket companies like SpaceX or giant utilities like PG&E that are affected by these things. And that is our business model, providing as a service our capability to them. That's our business model. It's early yet. We think it's a good model. It scales well, but obviously we need to extend our geographic coverage and our, if you will, spatial coverage.
Yeah, the DoD right now, and especially the United States Army, is all over electromagnetic protection and everything associated with it. They've, you know, from EMP, false Carrington events, and all of that, and what a tactical and strategic disaster it would be when those systems are compromised in any way. So there should be a bundle of funds in that zone. So does anybody compete with you, or are you in the sweet spot?
You know, there are organizations that use the model-based approach. There's no one doing nowcasting. There are lots of organizations doing, taking model-based approach and saying, you know, because quite frankly, when nothing is happening in the ionosphere, the average is pretty good, right? Not a lot. It's not a lot of time that happens, but you know, that's the state of the art. So so we compete with these established legacy systems that are well in place. And ours are, if you will, at the moment, at least on the fringes for those organizations where that real-time actual environment knowledge is important.
Are you restricted by any gaps in the sensors that you use in the sense that, you know, if you're setting aside the oceanic quantities of server calculations and stuff that you need, say you had unlimited funds and that was all taken care of, is there anything in the sensor or data source to feed your model that isn't quite there yet?
Well, again, we don't use a model. We just take in all the data, right? The data, that's
But the
our,
data is coming from, you mentioned a couple of satellites.
yeah, just a very,
Some of those
multiple-
constellations are better than others probably and do different things for you.
Absolutely. You know, like, you know, satellites in polar orbit have a refresh time, right? We would certainly love more. So the refresh time is, the repass time is, it's shortened. We like, you know, the fact that Amazon is putting complementing the existing ground downlink stations, putting together a global network for that, because we can get the downlink data much faster than, you know, once every hour or once every half hour. So yeah, we're limited by literally access to data at real time. That is the one challenge we have, because we need that data in real time or near real time. And we need lots of it. So, you know, as satellite constellations proliferate, as ground station capability expands, and as more and more sophisticated techniques emerge, we benefit. So we think the space economy proliferating and growing is going to be a big help for us. We're riding that wave, so to speak.
Hopefully Amazon took my suggestion at the NASA hackathon to use look into phased array steerable antennas instead of pointing dishes. Fortunately, there were two guys there from Lockheed Martin, you know, who integrate the Aegis system on the Navy ships, that were more than willing to talk to them about that. But there's that in the uplink and downlink segment is so incredibly restricted, you know, in terms of what can shovel through it.
I would agree. The uplink and downlink systems are slow, to say the least. And, you know, we take advantage of some other radar systems, and they're literally, it's passing tape. I thought tape was dead 20 years ago. Like, they're passing tape? What do you mean? And then, you know, you may have read the big downlink station island, Svalbard, in the North Sea. You know, the Russians just cut the data link to it. So, you know, the data, it's all about data. This is what you guys do, space hackers. It's about the data. It's just getting the data. How do I get the data? Give me more data. Give me more data in real time.
XKCD has a great cartoon about the magnetic tape and its density over distance and cost. And it's really interesting how it worked, how it actually does economically work out. Back to the at the current time, it's back to the sneaker now.
Please send me that cartoon because I would enjoy that.
I've run into it in the past when I was trying to get some Aster satellite data, and they had to get on. The Japanese Space Agency had to hand it to the Air Force that put it onto a KC-135 that flew to the Alaska satellite facility, where they then had to upload it so that I could eventually get to it. Actually, ASF, those people are really amazing. They just make it work. They make it happen. I was so impressed with them, the lengths that they went through.
That's cool. Very cool.
Go ahead, Joe.
So this is a little far afield, but maybe James will be pleased that I ask, is there something that maybe could happen on Mars that, is there such a thing? I know there's not much going on in the atmosphere of Mars, but there is a little bit of an atmosphere. Is there something that could be done there to give some ideas of, because we are planning, not this week, but maybe soon, more trips to Mars.
I actually don't know much about the climate of Mars and the atmosphere of Mars, so I would, I don't know if it has an ionosphere or a magnetic field like the Earth has. So I can't comment. I just don't know.
I'd be
James
happy to
just
take that
came
one.
back.
Mars does have a very thin atmosphere. It's 1/1000th of the Earth. It's mostly carbon dioxide. It does have a very limited magnetic field, although most of its magnetic field has been lost since the early days when Mars was, 4.5 billion years ago, once a warm and wet planet like the Earth. It's lost it's lost the majority of its atmosphere, and we think it was a result of it losing the magnetic field first. And people speculate there's something with, the geomagnetism overall of Mars. The iron core, the way the magnetic field is generated on Earth is because we have an iron core that's rotating. And Mars also has an iron core, but it may not be rotating anymore. And people speculate why that might be. And could we someday in the far future terraform Mars? And one of the first steps would be to try to get it back its magnetic field, either by literally restarting the core rotating somehow, or by doing some artificial engineering project to give it a magnetic field. Because if you just warmed up Mars and allowed the water to start coming out of the rocks, and the other carbon that's locked up in the surface, that would be great for having the atmosphere be thicker, but it would still be unprotected from the sun and the radiation of the sun, and eventually would lose that atmosphere just like it lost its first one. So it's an important kind of area to research more of and understand what happened in the past to make Mars lose its magnetic field and thus its atmosphere.
Interesting. Thank you for sharing that. I had no idea.
So that brings up a question here is, if Mars lost its field, we could lose ours. And would we know that we're losing it? Because it seems like it would happen pretty slowly.
Yeah, I think it would. I don't know. I would suspect it happens over millions of years or billions of years, right? You just said. So no idea.
That's kind of under question right now, because the magnetic pole migration has been speeding up and going in different directions, and like anything, accumulating more and more data over time at better and better resolution, et cetera. When they look at the magnetic signatures in rock formations and things like that, there is some evidence to suggest that, reversal can occur, and that it may not be as straightforward as previously thought. they're now doing seismic tomography through the Earth's core and getting a much better idea of the relationship of those large, I'm just going to say, I don't know what the term would be, magnetic influenceable masses that exist, you know, not evenly distributed within the Earth itself, and how they might influence that magnetic field occurring. So it's really a lot of new stuff, like in the past 5-10 years has come out about that.
Fascinating.
If we lost the magnetic field on Earth, we would be unprotected from the sun's radiation. And so, you know, humans would be in serious trouble.
Yeah.
For one thing, but we also, I think, would start losing our atmosphere over time. And yeah, that would be, you know, the Earth's magnetic field is really what, if you look at, you know, I've looked at various models that show how the sun, especially around solar flares, and I think you mentioned, was it the Carrington event? You know, major solar storms that hit the Earth, you can kind of see them hit and how the magnetic field of the Earth and the Van Allen belt sort of disperse it around the Earth. It's protecting us from the sun's solar flares and other coronal mass injections and things like that happen. And so, yeah, humanity would be in serious trouble if we lost our magnetic field around the Earth.
Yeah.
I'd just like to say I super admire the fact that I have not heard of you guys. And in this way, the zone you're in has like thousands of years of skepticism attached with it, even mentioning, you know, the possibility that you do earthquake reaction, et cetera, just automatically, and most, you know, most technically minded people, you know, raises a witchcraft scenario. So as going forward, you know, fighting that, and then just only talking to the people that matter, right? And building, you know, building that reputation, et cetera. It's not an attitude, it's an attitude completely opposite of the typical, got some VC funding, you know, make inflated claims till we build our net worth and then, you know, have it break. So, you know, awesome approach. It bodes well for your success.
Well, thank you for that. It's lonely, but thank you. You know, one of the things we're looking to do actually is, because I know you mentioned this, James, at the beginning, is, you know, we're looking to add to our team as well. So groups that are, you know, obviously data scientists are always good. We do a lot, you know, most of our technical team are physicists and mathematicians as well. But anybody who's really got an interest in kind of the esoteric aspects of what we're doing, we're always looking for the type of people. So if you hear of somebody, or somebody it piques their interest, please pass them on to us. We would appreciate it.
I would love to sell your thing.
Do you guys have a public website for people to reach out to you if they're interested in job opportunities?
We have a website, and there's a form submission there that you can put in. So yeah, absolutely. Michael, send me your email.
So your slides said in the lower, on my screen, it was the lower right-hand corner, that it was confidential. Is that confidentiality now void, now that we're videoing the presentation and going to put it on YouTube?
Yeah, no, that's fine. Those particular slides we've shared before. So
okay,
I'm good with that. That's fine.
Thank you for asking that, Joe, and thank you, Clive, for clarifying that. We are going to.
You bet.
YouTube. Thank you.
No problem. So yeah, anyways, gentlemen, I
Thank you so
sincerely
much.
appreciate the opportunity to talk with you guys. You know, you know, potentially, you know, there's just a lot of opportunities for data. Give me data. We love data. It's all about the data. So thank you for your interest. Thank you for the questions. The questions were fabulous. And you know, invite me to the next one, or the NASA hackathon, or whatever. I'd be happy to attend.
Yeah, we would love to have you for all of those events. And thank you so much for joining us today. And feel free to come back to this monthly series as a attendee anytime you'd like as well. And just a little bit about the Meetup series. This is our official website for Space Data Hackers. It's very simple. It's just like a hacker website. You can access the Meetup page right there, and that will have our next meeting, as well as our Meetup community. You can access our YouTube recordings here with the second link, join our Slack channel. And then finally, I want to highlight the wiki, because we're trying to build this out. This is a great set of resources. If you're new to this field, if you want to learn more about data science, working with data sets, machine learning, we have a lot of resources on this page. A few of us have spent quite a bit of time on it over the last couple of years. Some free courses you can take, many popular space-related data sets. I myself used the JMars data set that Michael Patrick once told me about in this Meetup series.
Cool, isn't it?
It's great, and it's great to visualize both the moon and Mars. It's fantastic. So anyway, yeah, feel free to access this wiki. Again, the website I showed you earlier is spacedatahackers.com. And we're also looking for folks to help build this out as well.
Absolutely. That's super cool.
Yeah.
I didn't know about all that.
And thank you for paying attention to the ionosphere, the red-haired stepchild of the atmosphere. You don't hear much about that.
No, tell more people, because everybody talks about deep space, but 95% of the satellites are in low Earth orbit.
Yeah.
So.
So this is the time of the Meetup where we like to highlight any community projects that folks would like to share. So if you've worked on something recently that you'd like to share the group, or maybe just talk about areas you'd like to learn about, now's the time to do that. And if no one wants to share anything, I can talk a little bit about what I've been working on. So.
Well, I have a question. I'm going to a hackathon on Saturday here in Tacoma, and it's being hosted by Blue Marine, which I think is it's a state funded and sponsored, well, federally funded and state sponsored marine business, and I think marine health focus. And so I was looking at the SOTO NASA website, which is the something ocean temperatures, and it puts up chlorophyll as one of the things that it can in the World Vision map. And the chlorophyll appears to come and go. And so I focus specifically on the Puget Sound, since I can kind of relate to what's going on here. And we have sensors here that can tell us what the weather is. And I noticed that the chlorophyll appears to come about 2 days after a rainstorm, and then so it rains and then it's sunny. And I don't know if that's a correlation or if I'm just making it up, because I just was looking at it, but I was wondering if anybody knows anything about chlorophyll in the Puget Sound and if there's any correlation.
Yes, there is. And what you're seeing there is after it rains, the runoff occurs, takes some time to accumulate to the groundwater, percolate into the streams and rivers, and then it flows into Puget Sound. The nutrients hit the sound. Puget Sound has kind of an odd stratification because it's fairly deep, and the temperature difference of the warmer water over the colder, as I recall, spreads it out in a thin layer on the surface. Sunlight, food, well, the little buggies, love that. So it causes, I think the technical term is a bloom. I don't know how
Yeah.
dramatic it is for Puget Sound, but in Florida, that.
Well, that's something for further research. That I just was hoping to get a little maybe edification there, and not edification, education. And I'll take it from there and study some more this weekend and see if hopefully there will be some people there from maybe the ecology department with the state, and they can answer some additional questions.
And feel free to email me, or we can have a Zoom call or whatever. I'm happy to help you with that.
Okay, thank you.
It's a good friend of mine.
All right.
Joe.
Any community projects folks would like to share tonight? Anyone has something? All right. Well, I am going to show you guys a little bit of what I work on these days. And I'm actually, I mentioned I'm with the Mars Society. We operate a research station in Utah called the Mars Desert Research Station. This is a project I've been involved with for about 6 years. This is a free VR app you can download on the Steam video game platform. And it is a digital twin of our Utah Mars Desert Research Station, which is built in a place that is a Mars analog, a place on Earth that's like Mars. That's in the southern Utah desert near Moab, if you're familiar with that area. And so I'm actually heading out there tomorrow morning for a 2-week Mars simulation that I've been planning with 6 other people for about 3 years. We are going to be living in the base as if we were living on Mars. We'll be wearing simulated analog spacesuits when we go outside, and we'll be working in all the different buildings. These are some of the different facilities we have. We have the Science Dome and the RAM, which is a repair, kind of an engineering work center. It's a Chinook helicopter body that's been repurposed. And this is the green hab. And we have a full green hab right now. There's basil and tomato plants and all these other herbs in there that we're going to take care of for 2 weeks. But then I'm also going to test out a new version of this VR app where we are going to actually plan out what EVA traverses we're going to do in Utah around the station the night before using VR. And then we also have these new devices called Meshtastic, which is actually an open source project. And these are little devices. This is one of the reference models. It's called a LilyGo T-beam. And so the idea is if you have a bunch of these out in the desert, you can build an ad hoc mesh data network.
Cool.
And so you could imagine having one of these on your suit, and you're capturing your vitals. You're also tracking how long you've been out and your oxygen level. And then the data will go all the way back through this mesh network back to the Mars habitat. And we have a server there where we're going to write this to the cloud. We're going to write this to Azure Log Analytics. And the VR app then can pick it up. So in effect, you could put on the VR headset, and this works on a regular Oculus Rift VR headset that's commercial off the shelf. You can pick these up at Costco these days. And you're going to put these on, and we can actually be in the Mars terrain, talk to each other. And if someone's out in the field, we can actually have a radio link with them through the VR app. So in effect, you can explore an area together, person out in the field and a person in VR. And you can also imagine using this, you could use this for field science if you had a senior geologist in VR and a junior person out in the field that can get direct assistance of what to explore, how to take samples and things like that. You can imagine this being used for remote engineering support. So the generator goes down and you're on Mars, and you've got a rookie engineer there, and he puts a suit on, but he doesn't know what to do to fix the generator. You can put on some VR goggles and see what he's basically where he is on the map, and help direct him there. And if you can imagine having like a VR representation of the hardware as well. So the rookie can kind of train in VR before he goes out, or you can help him in real time. So anyway, this is a project that we're really excited about. We're going to do a bunch of testing of in the next 2 weeks. I was at Yuri's night earlier this month, and we had a VR demo there as part of Yuri's night where we showed some of this. We had a little press event in the morning. So yeah, that's kind of what I've been working on. It's data related. We're kind of tying together, we're integrating all these different systems together. The VR app, the Meshtastic devices, Azure up in the cloud, got a Synology NAS server that we're going to put into the hab, and an Ubuntu VM on the Synology NAS that does some of the hosts some of the logic that makes all this work. So yeah, it's pretty exciting, and I'll next month I'll come back and I'll tell you guys how it all went.
That's fabulous. Amazing. How long are you going to be like in the environment?
So we have a 2-week mission, and that's a standard one for the Mars Desert Research Station program. We're crew 261. There's been almost 300 crews, 2,000 people in the last 20 years. So we'll be in there for 2 weeks, full 2-week sim. It's 12 days in sim, and we've been training for it. We're all very excited. Most of my crew is from Europe. A lot of them are flying in from France tomorrow. So we're really excited to do this.
That is so amazing. Good for you. Absolutely amazing.
Thank you. All right, guys. Well, unless there's anything else, it's good to see you all, and enjoy the rest of your evening, and we'll see you next month.
Sounds brilliant. Thank you again.
Thank you so much, Clive. Really appreciate it.
Absolutely. Thank you, all of you.